Good afternoon, everybody. Today, I select these topics from the last chapter, which is chapter 14, the periodic motion, and I'll try to finish them and start solving examples after finishing. Now, we will talk about periodic motion. If you notice my motion now, it is a period. We will talk about that. The motion going back to back and forth and back, it is a periodic motion. We will talk about describing what is the periodic motion. Okay. Also, section 14.2 will talk about the simple harmonic motion. What is it? Using equation. Also, we'll discuss the energy in simple harmonic motion, and also we'll see the simple harmonic motion for that describing the simple bundle. Yes. Already I upload the lecture sheets. You can't find them. Simple harmonic motion is very applicable in our life. For example, this motion is simple harmonic motion or periodic motion. Okay, because I'm repeating my motion along a certain path during a time. This is a periodic motion. My walking is simple harmonic motion. The pendulum, if you look at this is a simple pendulum, and yes, like this. Yes, like this you'll see it. This is a simple pendulum. It is moving via simple harmonic motion or periodic motion because it is moving along a path during a time. This is a periodic motion. Also, if we use, I will try to zoom in. Yes, great. We have the spring and the mass hanging in that spring. We have the weight downward and we have hook slow upward in that spring. If we apply by this motion, by this force, you will see that we have a periodic motion in mass spring system. And we can compute anything we need after seeing our equations. And you will do this, maybe you did it in the lab. You have a mass spring system and also a pendulum, a simple pendulum. You will do this experiment depending on the length and the mass constant and so on. So, as written here, when a body is or a moving particle repeat its motion along a definite path after a regular interval of time, its motion is said to be periodic motion. Okay. The description now. We know what is the periodic motion. We need to know some important properties of this motion. When a mass hangs with a spring, for example, and this mass is moved periodically like this. If we look at it and move the time line, you will see this motion. Look at my mass now. If I project the motion of this bottle here, it will be like this. Try this again. right? Now this sinusoidal motion is the mathematical description of the periodic motion or for the simple harmonic motion. So I'll use the x, y direction or the xy plane to understand some of my periodic motion. This is the displacement of my object, of the moving object. This is the displacement. We can name it x. And this is the timeline in seconds. Now we have a wave or a simple harmonic motion. This simple harmonic motion has many properties. For example, okay, I'll do this. For example, the simple harmonic motion repeats itself after a certain time. This is the time. This is the certain time. It repeats itself again and again and again. Okay, so this time we call it capital T. We deal with it from before, which is the period, which is the time period. For example, the period of rotation of Earth around itself, it's 24 hours approximately. Also, look at our experiment again. Sometimes our force is little like this. So our wave, it is small in altitude. Sometimes if we have more force, we have more. This displacement, the more displacement or the less displacement, we call it the amplitude, which is x maximum. We call it A, amplitude. Okay? We have an E on it. Also, what we have? This is the time period. This is the amplitude. If we draw it this way, if we draw it with x, or if this was y direction, not the time, we have the wavelength. We will not talk about the wavelength. We don't need it in our. Let me do this. Okay. What we have also. If I ask you, how many waves you see now? I'm asking. How many waves? We have 1, 2, 3. For each wave, we have a top and bottom, a maximum point and a bottom wave, minimum wave point. I'm sorry. We will not talk about these things also. We'll just learn about simple harmonic motion and simple wave. We have 3 waves. For example, if the time here is 1 second, so I have 3 periodic motions or 3 revolutions or 3 2 pi total rotations in 1 second. So our motion repeats itself 3 times in a second. This thing is called number, which is number of revolutions per second is the frequency. We measure frequency using hertz, which is 1/second. Number of waves over second. It is equal also to 1/second or second to -1. We hear hertz many times a day if we are hearing to the radio, because It is the unit of the frequency for the waves. Okay? Any question about that? The question? Okay. Now we have the frequency, which is number of waves or rotations in a second. And its sample is F. F is the frequency, which is number of waves per second. This will be equal as a mathematical or physical formula. It is 1 over time period. It is simple. Why I put 2 pi? I put 2 pi there because if we have also a circular motion on a disk and we have this mass, and this mass is rotating with velocity omega. If you look at this mass from a side, you will see it going up and down. I will rotate this. With respect to camera now, it is not just going up and down, but actually I'm rotating it, right? But if we look at it from outside, from a side, it is going up and down. It is a simple harmonic motion or a periodic motion. So any rotation with angle 2 pi is a full wave motion, a full period. Okay, from here to here, it is half a period, which is what pi over 2, which is the motion from here to here. I'm sorry, it is pi, just pi. This is 2 pi. Let us look at sheet number 2, if you have it. I'll draw the waves. Here we can see we have many types of periodic motion: a spring mass system, the earth around the sun, the clock hands. Okay, if we have this periodic motion, okay, this motion, this wave has the same amplitude. This is A for this one. Let us call it 1. And this is A1. This is minus A, by the way. What if we have another? I don't know about this color, but what if we have another simple harmonic motion or a periodic motion? Look at this. This wave, which is number 2, yes, has another A amplitude, which is A2 and minus A2. But what also about the frequency or number of waves per second? We see that the frequency of the second wave is more than the frequency of the first wave. And the amplitude of the second wave is more than the amplitude for the first wave. Any question about that? We are changing the time period. This is T2, but this is T1. Thank you. Get them, Yahoo. Okay, another way. What if we have this way? This amplitude A3, you can see it, I think, A3, and the frequency or the period, the time period is much longer than the first two. By that, I'm now telling you that we have, that's right, we have a periodic motion always in our study. But some of these periodic motion is slow, right? Some of them is fast. Okay, that's the, and the amplitude is depend on my force, like this. This way we break the constant K. And we ruined our experiment. We don't need it anymore, but we can use it. Okay, now, what else? The first thing we told you about it, the frequency is 1/T. We will solve an example on it. And we have another relation. When I'm telling you that we have a circular motion for a mass, for example, with velocity omega. Now omega, how much omega? Omega is 2 pi multiplied by r. Okay, but if r is 1 for a unit circle over the time period, this is omega. And by that, 1/T is f. So omega is equal to 2 pi f. Yes, salam. Now f is a frequency. 2 pi is a number. Are you asking me now, is omega a frequency? Is omega just like a frequency? It is yes. It is angular frequency. Okay, or number of rotations per second. So we have two kinds of frequency. Omega, which is 2 pi f, and f, which is the frequency. Omega is the angular velocity, what we know from before. We will use it in our examples. Look at this example now. I'm not supporting Brazil, okay? Now, not supporting anyone. Now, for the first example, I'm asking about the clock hands. We have the hours hand, and we have the minutes, and we have the seconds hand. For the seconds hand, this one, how much time it will take to make a full rotation? It is 60 seconds. So its time period for the second is 60 seconds, right? Because after 60 seconds, it gets back to its initial place. Then its period of motion needs 60 seconds. How much the frequency? It is 1/60. Here. It is simple. What about the minutes, its time period for the minute hand is 1 over 60 minutes multiplied by 60 seconds. Our work is all of our calculations in seconds. So it spent 60 minutes multiplied by 60 seconds, which is 1. No, the time, I'm sorry, not 1 over, that's the frequency. The time period is 60 seconds multiplied by 60 rotations for the minutes. It is 3,600 seconds, right? Now, what about the frequency? It is 1 over that number. Hertz. It's simple. What about the hours? And its time period, it is not 24. We are not talking about a day. We are not talking about just one rotation, which is the 12 hours. So it is equal to 12 hours. We need to convert it to seconds. We need to multiply by 60 minutes, then by 60 seconds. It is equal to 43200 seconds. From that, the frequency for the hours hand equal to 1 over that number, which is again 43200. Any question about that? We just saw the frequency and the time period for the clock hands. Another example on the graphic, in the graphical representation. Any question about that? This is X, and this is the timeline by seconds, and it's by meters, I think. It's okay, by meters. We have the time is divided 3 seconds, 2 seconds, 1 second. And we have 3 periodic motion. We have 3 waves. The first one is this. I am not caring about that amplitude, okay? The second one is this. You need to divide your path to draw it in a good way. The third one is this. I will make it bigger to be more clear. No, not here. So this is 2. No, this is 1. This is 2. And we have 3 here. As you see, we have 3 waves. This is the big one. No. From the beginning, I should draw it right way. This is 1, and this is 2. So now we have three ways. The first one, this is the first one, the smaller one. If this is 1 second, this is half a second. This is a quarter second. I'm asking now about the time period for the smallest wave. Smallest. How much the time period for it? We have the total wave after half a second. So T is 1/2 seconds. How much the frequency? It is the opposite, or 2/1. The second wave, the medium wave, this one. Its time period is 1 second. So this is the second one. The time period is 1 second. And the frequency is 1/1, which is 1. What about the third one? The biggest one. It completes its rotation after 2 seconds. So the biggest its time period is 2 seconds and the frequency is 1/2 hertz. Is that clear? Now, if you see any motion on a graph, you can't find the time period and the frequency by dividing over the time period. Any question online? Andrea? Okay. Now, I'll move to the next simple harmonic oscillation or motion. Look at me now. We have periodic motion. If I go there, then to that point, then to other point, and then to my initial point, and then I repeat this irregular shape of motion, it is just a periodic motion. But if our motion is regular and it is easy to be represented by mathematical formulas, then we can name it simple. We can describe it using equations. Okay? Now, let us start with this system. If we have spring mass system, we know from Hooke's law that the elasticity force, or F for Hooke force, is equal to, we ruined everything, to minus K multiplied by X. X is the extension or the expression, the pushing distance for the spring. Okay? Also, we know from our big father, which is Newton. This is Newton's force is equal to M multiplied by A. We are not talking about the vectors now, vector notation, because we are moving in x direction. We are moving just in one direction. So the both forces represent the same system. Then we can equal them to each other. Before that, we need to remember that m, the acceleration, is the first derivative of the velocity with respect to time. Also, it is the second derivative for the position with respect to time. Okay, now we have this main relation. We have F from Newton's law, which is equal to m d2x by dt squared, which is that one, is equal to this relation, minus kx. This is an ordinary differential equation or second order. We will not go to solve it. It is simple to be understood. By doing this, reorder it, then we will see that d2x over dt squared plus k over m multiplied by x is equal to 0. M, I just divide over m and I move this term to this side, it will be positive. This equation, you know that, may you know that x double dot d2x by dt squared is x double dot. But it's okay. Now, we can solve this equation by using this final relation. X is a function of time, is equal to a, everything will be simple now. Cosine omega t plus phi. Omega has a relation with Km. Omega squared is equal to K over M. This is omega, K over M. So this is omega squared. Phi is an arbitrary angle. If our motion, I will not move this. If we have a simple harmonic motion and we started if I start my motion from this angle, it is the starting point. If you remember from before, we write x is equal to x naught plus v naught vt plus something. X naught is the initial point of motion. I'm sorry. If you remember, we're talking about x is equal to x naught plus v naught vt multiplied by half t squared a. X naught is the initial point of motion. Phi here is the initial point of motion in our motion. Sometimes we take phi is equal to 0. This is 0. If phi equal to 0, then we put it here 0, and that's okay. This is phi. Okay. A is the amplitude, which is the maximum displacement for our motion. That is A. This is x as a function of t. It is x, A. X of t. If we derive x with respect to time, we know that from before, we will see the velocity, which is dx by dt. we are good in deriving. A is a constant. Cosine is minus sine omega t plus phi. We need to derive that argument inside with respect to t. This is a constant, 0, and this is omega. Give us omega. This is the velocity of the angular motion or the simple angular motion. We can derive also the acceleration. So the acceleration, you need to derive it again. The minus sign will stay as is. A will stay omega. We have another omega from inside. It will be omega squared. The sign will be cosine again. Yes, sir. Now we can test this solution in our equation. Remember our equation there? d2x by d squared by dt squared plus k over m. X is equal to 0. This is the acceleration as a function of time. If I put it, this is the acceleration. It is minus a omega squared cosine omega t plus phi plus k over m. X, it is a cosine. I told you that. We have minus a omega squared cosine a omega squared yes, I told you that k over m, it is omega squared. So we have two quantities. Each one of them is equal to the other with negative sign we have. Then this will be equal to 0, which is the initial equation that we have. So our solution is right for this equation. I told you that A is the amplitude, omega is k over m under the square root, which is the angular velocity. And you know that omega is equal to 2 pi f, and it is equal to 2 pi over t, which is that time period. What we have also, phi is the initial angle. In general, we assume it's sometimes 0. Look at this example. What is the purpose of these equations? And we will see that. If we have a mass is equal to 2 kilograms, I think. Okay, and it is hung with a spring. We have that. And the position function x of t is equal to 7 cosine 4t plus pi over 2. And I'm asking you about many things. We can solve it all and more. This is in centimeters. The motion in centimeters. How much the amplitude? It is 7. We can see it. It is x maximum. X maximum when cosine theta or cosine anything is equal to 1, the maximum value for it. The cosine. So 7 multiplied by 1, it is 7 centimeters. This is A, the amplitude. I'll remove this. It is all exist in the sheets. Okay. How much omega? We know that omega t, 4t, omega is 4. What is the units for omega? It is radian and angular velocity. per second. From omega, look what I can find, the frequency. Also, I can find the time period. The frequency is equal to omega over 2 pi, which is equal. Is it so? That's it. Omega is 4 over 2 pi. This is the frequency. What is the time period? The time period is equal to the opposite, or the 2 pi over 4 seconds. This is hertz. Any question about that? We can compute many things using the position function. And again, it is in x direction. We don't care about y or z. Or just in one direction, maybe our motion, in y direction. Okay, what we need to compute also. What if we need to know the K for the spring, the constant? We know this relation. Omega squared is equal to K over M. We know M. We know omega. Omega is 4. Omega squared is 16. K is unknown. M is 2. So this is over 1. From this, K is equal to 32 newtons over meter. The K is for the constant. What else? There is type here. No, there is no typos. What x? What is the position x at t equal to 0? We need to apply 0 there. It is 7 cosine omega, which is 4, multiplied by 0 plus pi over 2. This is 0. Then we have cosine pi over 2. Cosine 90 is 0. 0 by 7 is 0. Then x naught is equal to 0 centimeters. Now, if I ask you to find the velocity, it's okay. You can derive that. Before that, if I asked you to find the position at time equal 3 seconds, you just put 3 and find the position. If I asked you about that, velocity. The velocity, we need to derive it once with respect to time. The acceleration, we need to derive it twice with respect to time. And then we can apply any time to find the velocity at that time or the acceleration at that time. I will tell you something. The velocity is equal to negative 7 multiplied by omega, which is 4, multiplied by sine, this thing. The acceleration is equal to the minus side multiplied by 7 multiplied by 4 squared multiplied again by cosine. This thing. This is the acceleration, this is the velocity, and that is the position. You can apply any time here and you can find anything. This is a first example. Great. Now, I'll move to the energy of our system. Which is section 14 point how much? 3. Yes. As we know from before, we are going in that the mechanical energy, we need to call it E. due to energy. It is a kinetic energy plus a potential energy due to gravity plus potential energy due to elastic motion plus war or something else, anything. If we are working on a level and this level at the same altitude, we can take this position is the zero or the reference point. Then H at this point is equal to zero. This will make our gravity potential energy due to gravity is zero. We don't care about it. And spring, for example, system. Okay. Now we have two energies. So our energy is equal to the kinetic energy, which is half mv squared. We know that. And the potential energy due to spring, it is 1/2 k x squared. We did that from before. Remember that? We have a function of v. We have the function of x. We can put them here. The energy is constant, by the way. We will see that. It is equal to 1/2 m v squared. It is negative a omega sine omega t. I will assume phi is zero. I'm not caring about it. Square phi is zero. Okay. To make it simple, plus 1/2 k. Again, what is the position function? It is a, the amplitude, cosine omega t square. Phi is zero. We don't have anything else. Now do it. Then the energy is equal to 1/2 with minus sign, but the minus sign is squared. 1/2 m a squared omega squared sine squared for that thing, omega t, plus 1/2 k a squared. We don't have omega here. Be careful. Cosine squared omega t. What we need to do? We need to remember that there is a relation between omega and m and k. Omega squared is equal to k over m. I'll put it here. Okay, I will put it here. It is the same, k over m. Simply, I can cancel m with m. Now, the both terms are the same with the points. We have it is equal to 1/2 from both terms, a squared from both terms. We have k from both of them. Then we have sine squared plus cosine squared, and this is equal to 1. We know that. So the energy or the total energy is equal to 1/2 k a squared. A is the amplitude. It is constant in our motion. Look here. It is just constant. It is a number in our example here. K is a constant for the spring. Then the total energy is constant. Right? Okay. We can write, remove k, put omega squared over m. It's okay. Or omega squared multiplied by m. Using this. Now we have this triangle. I think it will be. We have omega squared is equal to k over m. So k is here. We have m omega squared. So omega squared is equal to k over m. M is equal to k over omega squared. K is equal to omega squared over multiplied by m. So the energy, we can write it in different ways. It is half a squared k, which is equal to m omega squared. This is another view for the energy, right? Again, omega, it is 2 pi f. We need to square it, which is equal to 2 pi over t, also squared. Then, if you know the energy of your system, you can find omega, and you can find the frequency, and you can find the time period. Okay? Any question online? Offline? Now, I will not solve an example. There are many examples, and I will solve. Because we need to go to the simple bundle. And then, if we have time, I will try to solve example. Talking about the vacation week, I will start preparing the review. And if I have a time, as I send you an email, in the email, I will record the solution for this review, and I also will prepare more examples to be solved in the final week. I will discuss the 2 lectures here, and you can combine me with the via Zoom, okay? And the last 2 lectures are just like a review for the final exam. I will solve examples, cover everything. As we see now, we finished the chapter 11 and chapter 14 in this week. And we are done with the material this week, and just we have a review and example in the final week. And I am sorry that this semester is finished. I was happy with you. I don't know about you. Also, the evaluation. The evaluation is done, and you can start evaluating this course. And also, you can put that this shirt is nice. Okay, the simple bundle, which is section 14.5. The simple bundle, which is this one. And by the way, we have the complicated or the not simple or the physical bundle. This is simple bundle. It is connected by a string, and the mass of this string is negligible, okay? It is cancelled. And we are dealing, this is not simple, by the way, it is rotating. You can see the mass is rotating now. The pendulum inside of the first level is not simple also. Not moving here. It is not simple. The simple pendulum, the mass should be a point mass. The length L should just move in a plane, not rotating in a like this, in a volume as a cone. This is not a simple pendulum. It is rotating around the cone. Okay. Okay. What about the simple pendulum? We have this mass, think this length is L, and this angle is theta. We have the weight, which is mg downward. If this angle is theta, I'm sorry. I'm very smart in that. I watched myself many times to do this. Okay. Again, this is our simple pendulum. We have a mass, the angle theta, the weight downward, the length of the pendulum is L. Now, again, if we take the extension of this length, this is theta again. We have the weight can be decomposed to the two components. One of them to this direction, which is weight cosine theta. And another one, if our motion will be, because the length of the pendulum is constant, then our motion will be on the edge of the circle. So the other force will be tangential force direction to the circle surface or to the circle edge. Okay, this is the weight. In this direction is cosine. In this direction is sine theta. Okay. Now, put in your mind when we use the Hooke's law, F here was minus K X, and we have Newton's law M A, which is D 2x over dt squared. The acceleration. F here is the generator of motion, which is the Hooke's force. It is the restoring force, which restores the mass to its initial point. For example, this is x naught. The mass will be oscillates about this point. Under this force, this is the main force in our system. And we put this to understand our physics. What is the restoring force in the pendulum system? Is it this one? Is it omega cosine weight cosine theta? When I decompose the force, now this one is omega cosine. It is equal to the tension in the wire, in the string, just this one. It will not move the object left and right. So our restoring force or our generator force, our main force in our system here is this one, weight sine theta. Okay, where is theta? This is theta. Can we find sine theta? Yes, we can. If we draw this triangle, this is theta. This displacement, if we look from downward, we will see the pendulum moving like this. Remember when I am rotating the object? You're seeing it just going up and down. If the pendulum is moving like this, from downside, you will see it just going left and right. So this is my x of t. This is my x. X is going left and right, and so on. Now, sine theta, it's simple. Sine theta is equal to opposite, which is x, over the radius, which is L. Yes, I am. Sine theta is equal to x over L. So my generator or my main force is equal to W sine theta equal to W x over L. W, what is W? It is the weight, which is mg x over L. From point to point, we can change our quantities. Now, this is our main force. Okay, what we need to put to understand the physics in our system? We need to use Newton's second law. Comparing this with Newton's second law, it is the same, should be in the same system. So, F from Newton's second law is equal to Ma, which is m d2x dt squared is equal to the restoring force. This is the restoring force to the negative direction. It is negative. It is equal to negative mg x over L. This is sine. This is the weight. That's it. Now we can cancel m with m from both sides, and I can move this to this side. So d2x by t dt squared plus g over L multiplied by x is equal to 0. Yes, we see this equation from before. Remember this? d2x dt squared is equal to now plus k over m x equal to 0. Before we name for the spring, we name it omega squared. Okay, we can name this omega squared. It is the same equation and it has the same solution. So for the pendulum or central pendulum, we have x as a function of t is equal again to a cosine omega t plus phi, and phi is the starting angle. A is maximum x. This is A, the maximum x. In my exam, I have a discount on this point. Okay. Okay. Also, omega, it is the square root of k over L. What is the velocity function? It is the same. Minus a omega sine omega t plus phi. Phi sometimes equal to 0. What is the acceleration? It is minus a omega squared cosine something. Where omega is equal to k over m and equal to g over L. This is in spring, and this is for pendulum. This is omega squared. I'm sorry. We can write many formulas. We can solve many examples. All are the same. We are using the same math now. Omega squared is equal to, in spring, this is in pendulum. I told you it is k over L. This is L over G, or G over L. G over L. The frequency. Omega is equal to 2 by f. F is omega. Omega over 2 pi. Which is the square root. Maybe I had a mistake when I talk about frequency and the previous question. Example, we have a square root. Omega This is omega squared. So it is 1 over 2 pi square root over k over m. Here, it is the same. It is 1 over 2 pi square root of g over m. You will see that in the lab. I don't know if you did it or not. Did you finish it? Not doing it now? It's okay. Yes, the time period. It is the opposite. It's 2 pi, the square root of m over k. This is 2 pi L over G. What we have also? We are done by now. The physical pendulum. If we just use any not simple mass, it is not point mass. The string here has a mass. This is a physical pendulum. You and me, when we are hanged with something and shaking ourselves, we are a physical pendulum. Yes, because we have a center of mass. We need to find the center of mass of that object. I will tell you now what we need to do, but we will not study it. We will not solve any example on it. We are done with the material now. We finish it. We need to solve more examples. We will do that. For example, this is a physical pendulum, and it is vibrating about this point. We need to find its center of mass. Then assume all of its mass here, and assume this is a string L with masses. And we will not deal with this. We will assume we are dealing with a point mass. That's it. We can't solve omega, tau, t, anything. Damped oscillation. The damped oscillation is very important to be used. You are engineers. When a car starts shaking, we need to stop this shaking fast enough to stop any corruption in that car. So if our vibration like this, the car will be ruined. Everything will be ruined if the motion stay like this. What we need to do is to kill this motion, to kill this amplitude. Make the amplitude goes to zero by doing this. By this way, our amplitude is going decreasing. This oscillation is a damped oscillation. Sometimes it damped by itself by friction. Sometimes we force it by putting some system in the brake, in the car's brake, to make it damp fast away. Did you understand? Are you understanding do you understand this point? This is a damped oscillation. I think you will see it in the lab also. But what happened is A going smaller and smaller, keeping the frequency the same. Sometimes the frequency is changing. That's it. Any question about that? We are done by the material. We finished chapter 14 or selected topics from chapter 14. I recommend you to look at the blocks on Canvas to organize yourself to study for the final exam. The final exam will be maybe from 20 to 30 questions, maybe 25 to 30 questions with 1, 2, or 3, I don't know, extra questions. It will be the same. I bring my questions from the material. I will not make myself strong to show you, just to make a show. And that's it. Any question about anything, any issue, you can text me using my phone also. You can text me if I am away from the internet or my PC. We can prepare anytime, the Zoom meeting anytime, even during the vacation. and good luck. Any questions so far? Any question? Okay, thank you. I'll end the meeting.
Thank you. Have a good day.
You too. Bye, Mazen.